If you've looked at my other videos, you've noticed I built a couple of other Nixie tube clocks. I've built one based on a Raspberry Pi. I've built one based on a parallax propeller. I built Nixie tube calculators. What's unique about this one is I used this RC 2014 Retrocomputer kit. So the RC 2014 is something you can buy from Tindy. There's a guy in the UK, I believe it is, named Spencer, who sells them, and it's a retro computer kit with a Z80 microprocessor, so you can build things kind of the way they did back in the 80s. And I bought the original kit, and I've added all sorts of boards. In fact, I think I've replaced almost all of the boards in it at this point with my own boards. If you looked at my blog post lately, you've seen, preceding this post, there's probably close to a dozen different posts describing each one of these boards. In this blog post, I'm going to sort of summarize all of that. So the first 15-20 minutes of this will be a very quick review. If you've already watched those posts, then you can kind of fast forward or skip through the schematics and get to the more interesting stuff, where I show where the boards are located in here and kind of how things are wired together, and then do the demo of the clock. This clock does talk, so it just said 4:57 a.m. It's in this case that I made at Pinocchio. It's easy to build these laser cut acrylic cases. Designed it myself. All the parts are in here. It runs off 12 volts. So let's move on and start going through the schematics. It's a large project. There's a total of 7 different circuit boards that make up the CPU and the peripherals, plus an 8th circuit board that is a backplane, plus 2 more circuit boards that are Nixie tube displays, plus a GPS board, a high voltage power supply. There's a lot of components that make this thing work, and I'm going to very briefly go through all of that and then do a little demo of it. So here's a block diagram of all of the parts that make this up. So we have to have a CPU. We're using a Z80 CPU. There's a clock, 7.3728 megahertz, that is the time reference for the CPU. The CPU is going to need ROM and RAM. We use an EEPROM that we can program ourselves for the ROM. For the RAM, we're using a 32K RAM chip. We need to be able to receive serial data from the GPS using a UP501 GPS receiver, and the serial data will come into this SiO2 board, which will handle our serial I/O. The SiO2 will give us 2 serial ports, so the other port we can use as a console. Now, the GPS operates at 9600 baud, so we need a time reference that can generate 9600 baud. We actually generate 9600 times 16 and then divide it by 16. So you can read on my website why it was necessary to do this multiply by 16, divide by 16 business. To generate that baud reference, we're going to use the Z80 CTC chip. That's a general purpose counter timer that we can program to generate timing signals. So these 2 boards here together will allow us to read our GPS. We're going to need a speech board that will implement our speech synthesizer so our clock can talk. We need some digital inputs so we can read some switches on the front panel. Those are co-located with the speech synthesizer board. There's a real-time clock board that can be used as an alternative to the GPS. In case you didn't want to use the GPS to automatically set things, you could run off of a real-time clock with its own time reference so that the computer could keep track of time itself. That would be the most authentic way of implementing this, to the time period where you would have had something like this. The real-time clock board also has some digital output functionality on it. I just co-located that there because I had space on the board. And those digital outputs are going to be used to drive the Nixie tube display boards. So I'm going to start going through the schematics. I've already done 11 blog posts. Most of them have videos, and they go into detail on the schematics for each one of these sub-assembly boards that makes up this this RC 2014 based Nixie tube clock. So I'm not going to go into very much detail in these schematics. I'm just going to point out the major components, and then if you're interested, please go watch a previous blog post or visit my website at www.smbaker.com, where I have all the schematics up, pictures of the boards, build notes, whatever you might need to help understand how this whole project fit together. Now, every one of these schematics, since each one of these schematics is going to be one board. So here's an example board. This is a serial I/O board that I did a while ago. Here's a compact flash board. What else do we have here? Here is a counter timer chip board. So I've got lots of these little boards. They all plug into a backplane. So this connector here will be on every single one of these schematics, and it represents the connection to the backplane. So it represents this long 50-pin header, and that 50-pin header plugs into the backplane. And that is how all of the boards talk to one another. Layout and pin assignments in the header were designed by the guy who designed the RC 2014 computer, and I have made all of my boards compatible. So basically these reflect the Z80 pins. So there's address pins, data pins, some control pins, read and write signals, 5-volt ground. It's a total of 6 pins that are extra pins, and I'll kind of use them for different purposes and different boards. So on to this first board. This first board is the CPU board. Now the RC 2014 comes with a perfectly good CPU board. I've changed it slightly for my own purposes, mostly for interfacing with some of my other boards. Basically, I brought some control signals down to the extra pins so that I could easily bring out bus ack, wait, halt. None of that stuff is important for this perspective. So just know that in this case, we have a Z80 CPU, and it's pretty much connected straight through to the backplane. There's a footprint on the board for an oscillator. I don't use that particular footprint. There's also a footprint for a reset button. I don't use that either. And this here is the completed CPU board. You can see it's got a CPU, the 50-pin header. So I did put in a couple pins to wire an external reset switch, and these jumpers block down here is for interfacing with my bus supervisor board, which I use for development, but we're not really going to cover the bus supervisor in this blog post. So the next board we need is a clock source to drive the CPU. The RC 2014 kit came with a clock board. I happen to have some of my own clock boards. My own clock boards are a little bit fancier, but I don't actually need any of the extra features for this project. So the one I used in this project is my single stepper. And the single stepper, here you can see the RC 2014 backplane. Over here is a crystal oscillator. The speed of the oscillator is 7.3728 megahertz. That's the speed we'll be operating the Z80 and its peripherals at. And there's a bunch of extra circuitry in here that allows the stepper board to single step the CPU, execute one instruction at a time, and then you push a button and it executes the next one. That's great as a feature in debugging. For running clock, you don't need to actually single step it. You just want it to free run. So the only parts that we're really using for the running clock is the oscillator. If you want to know more about the single stepper board, then I have a whole blog post on the website about the single stepper board, and with design and how it works, and it explains it pretty well. So this is a single stepper board, and for the purposes of this project, the one important component is the crystal oscillator. The rest of this is all dealing with single stepping and auto stepping. So next up, our Nixie 2 clock is going to need both RAM and ROM for the Z80 microprocessor. So I happen to have a board that implements both RAM and ROM on the same board. It's a little bit of a complex board because it was designed to do some bank switching. But the important thing to know is that it implements both a 64K ROM EEPROM chip banked into 16K Windows, and it also implements a 32K RAM chip. So that will allow us to have up to 16K of ROM, up to 32K of RAM. Here's the RC 2014 backplane as usual. Here's some OR gates used to combine the read and write signals with the memory request. This logic down here all has to do with bank switching, which isn't necessary for this project, but is necessary for my CPM project. So if you want to know more about the bank switching logic, which would allow you to have 64K of RAM instead of just 32K, then you can read more in that particular blog post. And here is a completed banked Ram and Rom board. The EEPROM is over here, has a piece of black tape over the window so it doesn't get erased by UV. There's 2 RAM chips, 32K each. We're only using one of those. All this circuitry over here is designed to do the bank switching, which is covered in a separate blog post. So next up is we need serial I/O. So the serial I/O board uses the Z80 SiO2 chip. It implements 2 serial ports. They're broken out on 2 headers, port A and port B. Port A allows us to have a console. The console is great for debugging messages, so when you're debugging the assembly program, you know, you can print something in the console, see what's going on. So port A was console. Port B will go to a GPS module. The GPS module will use to automatically set the time on the clock. There is a 74HCT138N 3D8 decoder that's used to assign an address to this SIO chip for a port number. And basically on most of my boards I will use this same circuit which has an 8-way header and will allow you to put your peripheral chip on any of 8 addresses. And in this project I believe I've put the SIO2 at address 80 hex. Also on this board is a footprint for an optional oscillator if you wanted to use a different oscillator for deriving your baud rates. You don't actually need that footprint. The other thing to note is that there are 2 different ways to derive the clocks for these 2 serial ports. You can either use the system clock, that 7.3728 megahertz clock that was derived from the clock board and used to clock everything else, or you can use one of these extra pins on the RC2014 backplane. And so the reason clocking is important is that we'll want to operate different baud rates. So the console port will operate 115,200 baud. That's a great baud rate for interfacing with your Windows PC. You could send characters nice and fast. We can derive it from the system clock by simply dividing that 7.3728 megahertz by the appropriate divisor inside of the SiO2 chip. Unfortunately, the GPS module can't operate at 115,200 baud. It needs to operate at 9,600 baud. So what we will do is we will jumper port B. Rather than deriving its clock from system clock, it will derive it from this E1 pin on the backplane. And then we will use another circuit in the next schematic to generate that 9,600 baud reference. So here's an assembled SIO board. Here's the SiO2 chip. Here's the 3D8 decoder. Here is the 8-way header, jumpered to 80 hex. And here are the ports. I believe this is port A and that's port B. Here's a couple jumpers that let you enable a 5-volt signal so that we can actually power a peripheral. So we will use port A as our console, port B as our GPS input. So that brings us to the counter timer chip. So the counter timer chip implements a total of 4 different general purpose counter timers that you can use as timing references for other peripherals. And basically what they do is they take a reference, so the system clock or an input, or just any kind of timing reference, and they will divide it by some amount. And then they will pulse a pin every time that divisor comes up. So you could take the system clock and divide it by the right amount to generate a 9600 baud reference, and then that reference can be used as the baud rate generator for the SIO board that we just showed. So we have the CTC chip, we have the same sort of IO port addressing logic as 74HCT138N, a 3-to-8 decoder, a jumper block that lets us put the CTC on any address. We will put it on address 90 hex, right next to the SIO. So we can take this trigger out 1, route it through the backplane and into the SIO, and then we can operate the SIO at 9600 baud. It's pretty much all there is to this board. There's also another footprint for an optional oscillator in case you wanted to tie the thing to some oscillator other than 7.3728 megahertz. But in our case, we'll just use the 7.3728 megahertz oscillator. And here is an assembled CTC board. See, it's got the CTC chip, the 3D8 decoder, the jumper block, and then some headers for jumpering the output to the appropriate extra pin. There's 4 pins that come off up top here in case you wanted to use the CTC outputs to derive some external component. I didn't actually need to do that. So next up, we have a speech synthesizer board. The speech synthesizer uses the SPO256-AL2. Let's see, I don't think I marked that on here. SPO256A-AL2. And if you've watched my other blog posts, you will know to be careful buying those on eBay because a bunch of the ones on eBay are counterfeit. Only buy from one of the sources that have been vetted, like I think I have a pointer to like speechchips.com, someplace like that on the internet does have legit ones. You can contact me if you need a link to find a legit one if you want to build this, or just watch my blog post on the speech synthesizer board. It's all covered very well in that post. So the SPO256A-AL2 is capable of talking in something like 64 phonemes. You can assemble these phonemes together to form words. Have unlimited vocabulary because you're building words out of phonemes. It outputs sound. We have a whole audio amplifier section. This comes right off of the Radio Shack project notes for the SPO256. Basically just an audio amplifier and a bunch of filtering analog stuff. Down here we have the same sort of 3-to-8 decoder that we use to put this on a port. I put it on port 20 hex. So it's easy to write to the chip. It has 8 data pins. We derive the chip select from the 3-to-8 decoder. But it has these status lines back to tell you when the chip is ready to receive the next phoneme. And we want to be able to read those. So I use this 74 HCT 245 end to implement an input port that can read those 2 lines. So writing goes to this chip. Reading reads what's on this chip, with this chip connected to the status lines from the speech synthesizer. So basically the way you use this thing is you read from it to make sure it's idle, then you can write a phoneme to it. It'll be busy processing that phoneme for a while, then it'll be ready to receive the next phoneme, and you just sit there and pull until it's ready to receive the next one, and then you write the next one. You pull, write, just like that until you have said your entire phrase. We only needed to monitor 2 status lines. That left 8 pins left over on this 74 HCT 245N. And so I broke those out to a header, and those can be used as just general purpose inputs. So I hooked some toggle switches up to them, and I can use them as front panel controls to influence clock. So the speech synthesizer board, here it is. There's the speech synthesizer chip. Here's the 3-to-8 decoder, usual header block. Here's the 74 HCT 245 that's used as the input port. Here's that 8-pin header broken out with kind of a right angle thing stuck on it to allow me to hook up my button switches. We do need a special oscillator for the speech synthesizer, so you can see that there. So my initial version of this didn't use the GPS. It just had an onboard clock reference, and you'd have to set it yourself. So I implemented this clock board. It used I think it's a BQ 4845 chip. That's this one. So the BQ4845 is this one. It's a easy to use chip for implementing a real-time clock on an 8-bit microcomputer. We have the very same 3-to-8 decoding logic that we've used everywhere else to allow you to put this on a particular port. There was some leftover real estate on the board, so I implemented an output port on this same board. The output port is over here using a 74HCT374N. So writing to one of these addresses will send things to the output port. Reading or writing from the other address will read or write from the real-time clock. Here's a picture of the real-time clock board. There's the BQ4845. Here's the 74HCT374N. 8-bit output port that you can use to control external peripherals, and the 3 to 8 decoder logic with a jumper block. Oh, almost forgot. Over here is a crystal for running the real-time clock, because the real-time clock needs its own time reference to keep time. So as long as you're building a GPS clock like this one, you don't actually need the real-time clock chip. However, you do need this output port, because this output port is what I've been using to drive the Nixie tube boards. So for that reason, I kept this board in my clock, even though my plan is to run it from GPS and not actually to use the internal real-time clock chip, just because we needed that output port. So we also have Nixie tube display boards. Now the particular Nixie tubes that I'm using are these IN12, IN12 tubes. I like them because you can easily get socket pins to plug them into a PC board, as opposed to something like the IN14s. You kind of have to solder the tube itself to the board. These things are gas-filled tubes. They operate off of around 135 volts. They're capable of displaying 10 different digits, so 0 through 9, and a decimal point. So on a display board there will be 4 digits, so there are the 4 digits. Each digit will have a driver, which is a 74141N chip, also known as a K155D, I believe. I think the ones I buy on eBay are the K155D variety. You get those from somewhere in Russia. You also get the Nixie tubes themselves from somewhere in Russia or the Ukraine. You know, usually some former Soviet country for both of those components. So the driver chip takes a 4-bit BCD input and outputs one of the digits 0 through 9 on the display. There's an anode resistor, which is used to control the anode current in each one of these Nixie tubes. So where we will get these 4-bit BCD values will be from some shift registers. So a shift register takes serial data and outputs parallel data. So 2 shift registers, since they're 8-bit each, that would be this one and this one, are sufficient to drive all 4 of those driver chips. We also have on each one of these a decimal point. We don't need the decimal point for the clock, but it's been useful in some of my other projects like a calculator. So we will use a 3rd shift register for the decimal points and some transistors to drive the decimal points. People like to put LEDs to kind of backlight the Nixie tube, so there's a total of 4 spots left on the shift register in the middle here, and I will use those to drive 4 LEDs. If you want, I've never actually populated those LEDs on any of my boards or tried them out because I don't really like mixing the LEDs with the Nixie tubes. So the way this is going to work, there's 3 inputs necessary to drive the shift register. There's a data, we call that SEER in. There's a clock, and there's a latch. So you will put a data bit on the serial in pin, and then you will pulse the clock, high to low or low to high, which I forget which it is, but 1 clock pulse will load that data bit into the shift register. Now these shift registers can be daisy chained. So the first one, it has a serial out, which goes into serial in the next one, and the serial out goes to serial in the next one. And then there's finally a serial out, which we run off the side of the board, and this will allow us to daisy chain the boards together. So we could connect an arbitrary number of tubes, 4 at a time, using these boards by connecting the output of one board into the input of the next board. And then we only need 3 data lines to run all of this, and we can easily run those 3 data lines from an output port in our RC2014. Here's the assembled Nixie tube clock. So back here is the power supply. This is my standard high voltage supply that I use for many of my Nixie tube projects. It supplies about 130 volts through this orange wire to the Nixie tube display boards. Also on board right here is a 5 volt switching regulator, which supplies 5 volts to the RC2014 backplane and is powered via a 12 volt barrel jack out the back. So over here we have the RC2014. I use the 8 slot backplane. The rearmost connector I angled out the back so we can have kind of an expansion port, and we can plug in other boards if we want. The other 7 boards are all populated. So the first board is the speech synthesizer board using the SPO256A-AL2 chip. You can see it has some wires that come out here, this green and yellow, that go over here to the speaker. The speech synthesizer board also has a general purpose input port, which is these wires here, which hook up to these 3 switches that let me control various modes on the clock. The next board back is a clock board. I happen to use my single stepper clock board. Though just about any clock board will do. The default RC2014 clock board would have worked fine if I'd wanted to use that, but I just had one of these single stepper boards handy, so I used it. Obviously we don't use it in single step mode, we just use it in free running mode. Next up is the real-time clock board. The real-time clock board includes an output port, which is this connector here, and it has 3 signal wires, a clock, a data, and a latch that go to the Nixie tube display boards. Also power and ground for the Nixie tube display boards. The real-time clock itself is this big chip here. We don't actually need that if we're using the GPS clock, because we could just pull the time from the GPS. But if you wanted to operate without the GPS, you could rely on this clock chip and it would give you an accurate time reference. So this next board is my CPU board. It is my own design, though it's in this case it's not actually significantly different from the one that comes with the basic RC2014 kit. There is a spot on it where I was able to put some headers on the CPU board and run a cable over here to the reset switch so we can reset from the front panel. So this next board is the banked Ram Rom board that I originally implemented for the CPM computer. This design would have worked fine with just a separate RAM and a ROM board like the basic RC2014 kit, but I ran out of slots on the back plane. The separate RAM and ROM boards would have taken 2 slots. I just ran out of space. So I was able to use my banked Ram Rom board. Only takes up 1 slot and has the RAM and the ROM on the same PC board. So back here we have the CTC and the SIO boards. They go hand in hand together. So the SIO board has 2 serial ports. Port A is this one here that's unpopulated. It runs at 115,200 baud. You can plug an FTDI adapter in to get a console port. You don't actually need a console port to run the clock, but it was handy when doing the assembly language development to be able to output debugging messages to the console to see what was going on. So port A for the console is unpopulated unless you want to plug it in and use it. Port B hooks to the GPS. If memory serves, that was the UP501 GPS module that I got from SparkFun. Now the GPS comes up at 9600 baud by default when it's powered on, and that is the reason why we need the CTC board. The CTC board generates the 9600 baud clock. This uses a reference for the baud rate for this serial port. I think it actually, if memory serves, it generates it at 16 times higher than 9600. Then the SIO divides that by 16, and that's you multiply it and divide it by 16 for that purpose so it can do its bit sampling. on the incoming serial stream more accurately than had you just sent 9600 from one to the other. Up front, we have the two Nixie tube display boards. Those have a series of shift registers, and each one has 4 IN12 Nixie tubes. Since this is a 6-digit clock, we don't need 2 of the tubes, so when it's running, we just leave this tube and this tube blank. So let's talk a little bit about the software that's going to drive this clock. So the software is all written in Z80 assembly. So I've assembled it, I've programmed an EEPROM, put the EEPROM in the computer, and it can execute that, and that will execute the control loop for the clock. So there's a big loop. This is a looping construct. It goes around in a big circle, constantly waiting for things to happen. So what kind of things could happen? Well, someone could press a button on the UI. So if you push the button that says, I want the clock to talk, then the control loop will branch out here, and it will take the current time and turn it into phonemes. So take the time and translate it into English speech, you know, the components that make up speech. It'll put those phonemes in a buffer, and then it'll go back to the processing loop. The next sort of thing that could happen, there could be a character from the GPS. So the GPS is constantly outputting packets. One of them packets is the GPGGA packet. That packet includes the current time. So what we will do is every time there's a character, we'll jump to a subroutine, and that subroutine will kind of parse that GPGGA packet to extract the time. And then as we parse that one character at a time, we return back to the main loop. So the next thing in the main loop, a parse could have been completed. So this thing up here could have completely parsed the GPGGA packet, and the current time is known. If the current time is known, then we're going to jump out here to a subroutine that sends the current time to the Nixie tube boards. After we sent it, return back to the control loop. Finally, we have to process the phoneme buffer for the speech synthesizer chip. So you recall up here at the top of the loop, if you push the talker button, it jammed a bunch of phonemes into the phoneme buffer that constituted the speech for the time. So we have to output those phonemes one at a time, and the speech synthesizer, it can't hold them all. It can only hold a limited amount. I think it can say one and buffer another. So we have to kind of send them to the chip one at a time and wait for the chip to be ready. So down here we check and see are there phonemes in the buffer that need to be said? If there are, is the chip ready to receive a phoneme? If it is, send the phoneme to the chip. Then return to the loop back around, and repeat all these steps. Just keep doing that infinitely, and as new time packets come in from the GPS, we will process them here. As they are parsed, we will update the display there. Okay, we're ready to try out the Nixie tube clock. I've got a standard 12 volt switching power supply here, wall wart type thing. We'll just plug it into the back. When it comes on, you'll notice it's not displaying any time yet in this because the CPU hasn't actually been reset. The RC 2014 kit didn't include a power on reset, and I didn't implement one myself. I've always just, been hacking away at this and push the reset button when I want to reset it. Obviously for a clock, at some point it would be nice to actually have it so that when the power goes out and comes back on, it resets automatically. I'm going to have to take a little time to look into various reset circuits. But there is a reset switch that I ran out to the front panel. So when I push this, it will reset the CPU, and it will attempt to output the test pattern, which is 1, 2, 3, 4, 5, 6. Because I do have it automatically doing time zone conversion, it will probably decrement the hours by 7 hours because I'm in Pacific time zone. And so we should expect there to be a 5 displayed there. So it should be probably do 0, 5, 3, 4, and then 5, 6. And you'll see that for just a split second until it gets the packet in from the GPS. So let's push that. There was the test pattern, and there now it got its first GPS packet with the current time. and it's running synchronized to the GPS. So every time a new GPS time packet comes in, it updates the display. So over here, there's 3 switches. So the bottom switch doesn't do anything yet. My plan is that it will eventually be maybe a switch between the GPS that we can have automatically synchronized, or to run from the internal BQ8485 real-time clock. So I guess just for nostalgia's sake, it would be nice to have a pure a retrocomputer implementation that just ran off its own clock and didn't have this modern GPS module tucked in behind. So that's what that bottom switch is going to eventually do. The middle switch switches time zones, so I could switch between daylight savings and not daylight savings. If I was smart enough, I could program out that algorithm in software. Since the GPS does include date, we could have it automatically switch. Every time I've ever tried to program something to do automatic daylight time switching, I've screwed up the algorithm. So I need to take the time to do it automatically, but it's also easy to just flip a switch twice a year. That might be good enough. The top switch is going to say the current time. It'll say the hours and minutes, and then it'll say either AM or PM. So let's push it and see what happens. So what it said was 2:55 p.m. Let's hear it a second time. The PM and AM sounds very similar on this, so I might reprogram it at some point to say, you know, afternoon and morning or something. But for now, that's what it says, and let's wait until it rolls over, and we'll hear it say something different once it hits 2:56. So let's hit it again. So it said 2:56 p.m. And that's basically it. That's the new Nixie tube clock. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.